Uh, Welcome everyone. Good evening. So this is the 11th problem solving session for the NPTEL course Aircraft Propulsion. So this is like the penultimate interactive session for this course. So introduce myself again. I am Onindo, PhD candidate and a PMRF from Aerospace Engineering Department at IISc Bangalore. Uh, so so today's topics of discussions are turbines. We'll be discussing two problems and questions on two types of turbines: axial flow turbines and radial inflow turbines. Okay, so in the last 2 weeks, what we have seen that we have done thermal analysis for compressors. We have looked into centrifugal compressors and axial flow compressors. So as we have known that compressors are work absorbing machines, so we have to so the rotor does work on the fluid, right? And in the turbine it's the opposite. Turbines are work producing machines, and this axial flow turbines um, is the flow is mainly axial, which is like the turbine counterpart of axial flow compressors, and radial turbines are the turbine counterpart of for the centrifugal compressors, right? Okay, so it's like the analysis and the velocity triangles and all those things look similar, so we'll see how that goes. Okay, so before we move ahead, if you have any questions or doubts related to previous sessions or anything in general, else we can begin. Okay, all right, let's start. So first I have a series of MCQs and related to axial flow turbines and radial flow turbines, and at the last we have a numerical on axial flow turbines. Okay, so the first question: in case of axial flow turbine, the rotor blade passes acts as nozzle, diffuser, pressure increasing device, none of the above. So which is correct here? You can, as usual, you can type in the answer, your answer in the chat box. Yeah, right. So in case of axial flow turbines, you know that this the rotor blade passes acts as a nozzle. Okay, so to all turbines in that, when we have a turbine, we'll we'll see something like this. So this AI, okay, so we'll see that AI is greater than AE. Okay, so mainly the for the flow through the turbines, the flow is nominally um, um, subsonic. Okay, so this is your turbine. So you have seen that. So the flow passage, so the flow area sort of uh, decreases as the flow goes through the this rotor blade passage. Okay, so this sort of, so I say the rotor blade passage for the turbine acts as a nozzle, and for the axial flow compressor case, this I discussed in the last week as well. So we'll generally see that the flow area, so this is AI and this is AE. Alright, so AI is less than AE. Okay, so this compressor, these are again the rotor blades. So rotor, in this case the rotor blade passage acts as a diffuser. Okay, this is how the blade area of the blade pass rotor blade passes look like for turbines, axial flow turbines and axial flow compressors. Okay, so for turbines is generally the passage area is converging, it decreases in the flow direction, so it acts like a nozzle. Okay, and the for the compressor the flow area increases, so it acts like a diffuser. Okay, so it's generally the case. So this remember these diagrams I have drawn as like is generally the flow is subsonic, so this is true. So remember when we discuss nozzles and diffusers that depending on the Mach number of the flow, the converging area duct or diverging area duct can behave as both nozzles or diffuser. Okay, since here the flow is subsonic, Mach number is less than 1, so in nominally, so the converging area passage which is in our the rotor blade pass for turbine, it acts as a nozzle, and the diverging area rotor blade passage for compressors, that acts as a diffuser. Okay, alright, so moving on to the next question. In the velocity triangle of an axial flow turbine rotor, the relative velocity component, what happens to relative velocity component? It decreases. Option A, decreases from inlet to outlet, increases from inlet to outlet. Option C, remains constant. Option D, can't comment. Which is the correct answer here? Okay, all right. So no, if the relative velocity component remains same, it's like it can't, the you have to look at the velocity triangle. Yeah, yes, it increases. Okay, so just one simple explanation for this without drawing the velocity triangle. We have seen in which I discussed in the previous question that the rotor blade passes for turbines acts as a nozzle. Okay, so the remember, so it is acting as a nozzle. So when it's nozzle, the basic working principle of nozzle is that the flow velocity increases as the fluid passes through a nozzle, right? But remember here this rotor blades means these are rotating, right? This is the blades, the blades are rotating with the rotor. Okay, so the velocity component which that is like with relative to the motion of the rotor blades, that is the relative velocity component, right? So that will increase through the turbine blades. Okay, because it acts as a nozzle. Okay, so you know that because this is a what you can say here is this is a rotating nozzle, this rotor blade passages, this is a like rotating nozzle, so the relative velocity component that will increase as this passes through the this nozzle. Okay, and then but similarly in case of axial flow compressors, the rotor blade is like an rotating diffuser, so the relative component decreases, relative velocity component decreases as the fluid passes through it. Okay, so the component that remains constant is the we can say is the axial flow velocity, component, or the blade velocity. So because in axial flow turbo machines we draw the velocity triangles at a constant radius, so the blade velocity at both outlet and inlet and outlet stays constant, right? And also the axial velocity component stays constant. Okay, let me draw the velocity triangle. So this is one stage of a we can say axial flow turbine stage. Okay, so this is axial flow turbine. So this is like the nozzle which is like the stator blades. Okay, so the blades which are fixed, and these are the rotor blades which are rotating. And generally, so this is different from your what we have in our compressor state. So compressor say rotor comes first, then the stator blades, but in case of axial flow turbine stage we have first the nozzle or the stator blades and then the rotor blade, so the station numbering is slightly different. So we will be drawing the velocity triangle across the rotor. So this is 2 is the rotor inlet, so again we draw everything at a mean radius, right? So this the blade velocity at this location is constant because the blade speed or the rotational speed of the blade that is just depend that depends on the radial location, right? So first we have this thing. So this is, you can say this is u2 is equal to u3 is equal to u. Okay, so then we have the relative velocity at inlet v2, and we know u plus v gives the c. So this is our c2, the absolute velocity at inlet. So and then we can draw the angle. So this is beta 2 and this is alpha 2. All right. Okay, so then this is the inlet velocity triangle. Okay, so at the outlet velocity we have u, again the blade velocity is same, the u is same. Then here we have okay, so then so this is now our v3. Okay, so this is v3, and then u plus v3 should give us c3. Okay, so again if I'll draw the angle, so this is alpha 3 and this is beta 3. Okay, so beta is the angle that the relative velocity vector makes, and that is also the blade angle. Beta is a blade angle and alpha is our absolute velocity angle. Okay, so here you can see that again if you look at the length of the vectors, that v3 is greater than v2. Okay, so that we can say that relative velocity component increases. Okay, and if you look at the length of the absolute velocity vectors, you will see c3 is less than c2. Okay, so absolute velocity decreases. Okay, so this is for this is for an axial flow turbine rotor. Okay, so this, and but when, if you remember, for the axial flow compressor rotor, the trends reverse. The relative velocity component decreases and the absolute velocity component increases. Okay, and so this is your, so if you take the projection of the absolute velocity in the axial direction, so this is the axial flow direction, so this is your equal to ca. So this is your axial velocity component, right? So you see this is like, if you take the projection of the absolute velocity vector in the vertical direction, which is the axial flow direction, right? So you will see that the both projection of both the vectors c3 and c2 is ca. Okay, so the axial, that's why the axial velocity that is an assumption, or during the design we make, that the axial velocity component stays constant across the rotor stage. Okay, so when it is asked which component stays constant, it's the axial velocity component or the blade velocity, both stays constant across a rotor. Okay, while the relative velocity component increases and absolute velocity decreases across a rotor stage. Okay, so the correct answer here is option B. Okay, all right, any doubt? So this is so this is like the velocity, drawing the velocity triangles correctly is very important for this turbo machine analysis. So yeah, should be able to draw that correctly, so, and distinguish what is changing and all for the when you are doing it for compressor and when you are doing it for turbines. Okay, any doubt? Hope this is clear. Okay, let's move on to the question 3. From the velocity, sorry, I didn't get your question. So this no, nozzle also, in nozzle you will see the this part, right, between 1 to 2, right. So in nozzle you will see that this so if absolute velocity changes, so this is, let's say, the absolute velocity. So your C2 will be larger than C1. C is the absolute velocity. So nozzle at the, so the stator blades are the nozzles. So nozzles have this static like the blades which are stationary, right. And so when the flow goes to it, the flow velocity will increase. Okay, all right, and the absolute flow velocity will increase, and then the your yeah, then again in the rotor passage it will decrease. Okay, all right. Yes, axial velocity will remain same throughout the turbine. Yeah, CA is same. So CA1 is equal to CA2 is equal to CA3. Okay, all right. And also generally C3 becomes equal to C1, because the velocity that is coming out from the rotor, that will go to the nozzle of the second stage. Okay, so that's why the C3 generally is equal to C1. Okay, okay, because the C3 that is coming out of the rotor, that has to go to the nozzle of the next stage. Okay, and there the velocity has to be C1. Okay, so this is like this stage gets repeated, the same stage is an unit, so it get repeated. Okay, and we can have a number of stages depending on the pressure ratio, pressure drop required across the turbine. Okay, anything else? Okay, thank you, let's move on. Okay, so the next question, from the velocity triangle of an axial flow turbine, which of the following expressions is equivalent to tan beta 3 plus tan beta 2? Okay, so 2 and 3 refers to the inlet and outlet conditions of the rotor respectively. Okay, so CA is the axial velocity, U is the blade velocity, beta is the blade angle, and alpha is the absolute velocity angle. Okay, so let me draw the velocity triangle again, so quickly. So this is our V2 C2, right, and then this is our V3 C3, and the angles are, this is alpha 3, this is beta 3, this is beta 2, and this is alpha 2. Okay, so now from the geometry of the from geometry of velocity triangles, we can get these two relation, that is, so again, and one thing is that this is your equal to CA. Okay, now if you just do some trigonometry, we'll get these two relation. U by CA is equal to tan alpha 2 minus tan beta 2. This is from the inlet velocity triangle. Okay, and from the outlet velocity triangle you will get, that is U by C2 is equal to tan beta 3 minus tan alpha 3. Okay, all right, so these are the kinematic relations that you get from the geometry of velocity triangles. Okay, so also remember the carefully the kinematic relations that you get from the velocity triangles for axial flow compressors. Okay, so in that it is actually the sum of tans. Okay, but here it is the difference. Okay, so now since both these two are equal, you can rearrange this. You will get that tan alpha 2 plus tan alpha 3 is equal to tan beta 2 plus tan beta 3. All right, so this is what we get from the geometry of the velocity triangle. Okay, so now the question asks, which of the following expressions is equal to tan beta 2 plus beta 3? So that will be equal to tan alpha 2 plus alpha 3. Okay, so the correct answer will be option B. Okay, Clear? So these kinematic relations are very important, that and that needs to be invoked at times while solving the problems as well. So you should just remember this very carefully for this axial flow turbines, and also what happens for axial flow compressors. Okay, we have to be very careful about the station numbers and of the signs. Okay, even if you are able to if you can draw the velocity triangles correctly, you will be able to get this right. Okay, all right, any question? Okay, or else you can move on. Next thing, question 4: which of the following action options is correct for the rotor of an axial flow turbines? Okay, so let's look at the each of these options. Okay, so option A says absolute velocity increases. Is this correct? Is this true or false? Okay, we'll bring up the velocity triangle. Absolute velocity, what happens to absolute velocity? Yeah, it's false, because absolute velocity increases. Okay, option B, relative velocity component is decreased. Is this true or false? What happens to relative velocity? So this is also false. Okay, so okay, the option C, this is right, because we have seen axial velocity remains constant. Okay, all right, so this is just related to whatever we discussed about the velocity triangle. Okay, let's move on. Okay, so question 5: for an axial flow turbine, which of the following expressions is correct for stage stagnation temperature rise delta T0s? Okay, suffix 2 and 3 represent the inlet and outlet conditions as usual. So delta T0s is our stage temperature rise, Ca is axial velocity, U is blade velocity, beta is blade angle, and alpha is absolute velocity angle. Okay, so you have to select the correct expression for this. Okay, let's see. Okay, so the specific work output, we first write the specific work output. Okay, so for a axial flow turbo machine, we have seen that the specific work output is equal to the blade speed times the change in our wall component of velocity, right? So if I go back to this velocity triangle, and let's say I draw here the wall components. So this is our CW3, and this is our CW2. Okay, and if you see here that the directions of this these components, the wall components, are opposite. Okay, so the change in the wall component will be the sum of their magnitudes, sum of the magnitude of wall component of velocity. Okay, so that's why here we can write this is equal to U times CW2 plus CW3. Okay, ideally so we are adding up, because again the direction of wall components are um, opposite to each other in case of axial flow turbines. Okay, so you can see this is like CW3 is directed towards the left and CW2 is directed towards right. Okay, if we just consider the vector. Okay, so directions are opposite, so the change in the wall component of velocity, that adds up. Okay, and if you look at the again the trigonometry, will see that this CW2 is equal to Ca times tan alpha 2, and CW3 is equal to Ca times tan alpha 3. Okay, so this is, let me go back. So now let's say you take tan alpha 3, so tan alpha 3 is equal to this CW2 CW3 divided by Ca, right? So that's how similarly we'll get, so that's how we get the wall component is equal to axial component times the tangent of the absolute velocity angle. Okay, so Ws we get UCA tan alpha 2 plus tan alpha 3. Another expression can be, we have seen from the previous question 3, that tan alpha 2 plus tan alpha 3 is equal to this expression tan beta 2 plus tan beta 3. So that's how this is also true. You can also write this equal to tan beta 2 plus tan beta 3. Alright, so these are the expressions for the specific work output using the Euler's turbomachinery equation. Okay, and that is equal to our this Ws is equal to also equal to Cp times our the change in stagnation temperature. Right. Okay, so this is from thermodynamics, that specific work is equal to Cp times the stagnation temperature difference. Okay, so now if we equate both these two, we will get that delta T0s is equal to UCA tan alpha 2 plus tan alpha 3. Another thing is UCA tan beta 2 plus tan beta 3. Okay, so sorry, we will get a Cp here by Cp tan beta 3 by Cp. Okay, so if we now look at, so these are the two possibilities. So if we now look at all the options given, we will see that option A matches the expression that we derived. Okay, right. So therefore we can say that this so option is the right answer. Okay, so is this clear? So also, like, compare the expression that we get here to the expression that you get in when you do for axial flow compressors. Okay, and be mindful of the signs and the station numbering there as well. Okay, any questions so far? Okay, all right, let's move on then. Okay, so question 6. So here it is asked, which of the following expressions is the correct relation between the blade loading coefficient and the flow coefficient for an axial flow turbine? Okay, so what is, let's go through the definitions. So blade loading coefficient xi, okay, that is equal to the specific work divided by half u square. Okay, so that is the definition for blade loading coefficient. Okay, generally we do u2 square, but since for a turbine u2 is equal to u1 equals like u2 is equal to u1 is equal to u3, so that is u square. Okay, so we can just write it here, that is, let's not complicate things. Okay, so that is equal to half u square. Okay, so this is the definition for blade loading coefficient, and the flow coefficient phi, that is equal to Ca by u. Okay, so that is flow coefficient. Okay, so when we do flow coefficient for axial flow turbo machines, we use the axial flow velocity axial flow component divided by the blade speed. When you do the flow coefficient for centrifugal compressors or radial turbines, that is the radial component of velocity divided by the blade speed. Okay, so that's the difference when you compute the flow coefficient for these two different types of turbo machine. Because in centrifugal compressors or radial turbines, the flow is nominally radial, so that's why you take the radial velocity component. And in case of axial flow turbo machine, the flow coefficient is Ca divided by the blade speed. Okay, so let's now start from here. So this is Ws by half u square. So the expression for Ws, you saw that is UCA tan alpha 2 plus tan alpha 3, right, divided by so we can take 2 on the numerator, and that is u square. Okay, so we can cancel 1 u from the numerator and denominator, so what we get is 2 Ca by u tan alpha 2 plus tan alpha 3, right? And Ca by u is our flow coefficient phi, so that is, this is tan alpha 2 plus tan alpha 3. So this is one relation, and again we can use the tan alpha 2 plus tan alpha 3 is equal to tan beta 2 plus tan beta 3, right? So we can also write phi is equal to, sorry, xi is equal to 2 phi tan beta 2 plus tan beta 3. Okay, so these are the two expressions we have. Okay, so from the given options we see that option D is the one that matches. Okay, so option D is the correct answer. Okay, all right. Okay, let's move on then. This is clear. Okay, okay, so the question is, blade coefficient of axial flow turbine is higher than axial flow compressor, is lower than axial flow compressor, remains constant as axial flow compressors, none of the above. Okay, okay, so let's just look at this. Okay, so for that we did the analysis for axial flow turbine. So for axial flow turbine we have seen that the blade loading coefficient, which is again ws by half u square, that we got as 2 Ca by u tan beta 3 plus tan beta 2. Okay, so at 2 is the rotor inlet, right, and 3 is our rotor outlet. Okay, so for the axial flow compressor, if you remember, so axial flow compressor we generally denote 1 as rotor inlet and 2 as rotor outlet. Okay, so and so again there also blade loading coefficient is equal to ws by half u square. So there ws, you will see that ws becomes equal to uca tan beta 2 minus tan beta 1, okay, divided by or tan if I am not mistaken it will be, I guess, tan beta 1 minus tan beta 2. Just let me check this, might be mistaken. Yeah, tan beta 1 minus tan beta 2, okay, divided by 2 u square. So this will get phi as 2 Ca by u tan beta 1 minus tan beta 2. Okay, so you see there in general this for axial flow compressors, the term that we have is as a form of difference between two tangents of two angle, while in case of the blade loading coefficient for axial flow turbines we have the sum of two tangents. Okay, so from that we can say that the blade loading coefficient for axial flow turbine will be higher than that of axial flow compressors. Okay, is this clear? So it's just by looking mathematical at the two expressions. Okay, so we here in for axial flow turbines we have the sum, but in axial flow compressors we have a difference, right? So that's why we expect the value of the value of xi, the blade loading coefficient xi, that should be higher for axial flow that will be higher for axial flow turbines. Okay, is clear? Okay, you can move on. Question 8. So this is also again related to velocity triangle of axial flow turbines. Okay, so we have to select which of the following options is true. So I will give you some time to go through the options and and just tell me which is the correct and which is the correct option. Just go through the options correctly. Only one is, and can type the answer in the chat box. Yes, option C is the correct answer. Okay, so what it says that axial velocity at outlet is lower than at inlet. So let me again write this. So axial flow turbine rotor. So axial flow turbine rotor is like 2 is the inlet and 3 is the outlet. So the absolute velocity is lower, so C3 is less than C2. Okay, the relative velocity is higher, V3 is greater than V2, and your blade speed stays constant, right? U3 is equal to U2 is equal to U, and also the axial velocity component stays constant. Okay, so now if I write the same thing for axial flow compressor rotor, so where 1 is the inlet and 2 is the outlet, so you will see that the outlet velocity component is higher, outlet relative velocity, so outlet absolute velocity is higher than the inlet, outlet relative velocity is lower. Okay, and again the blade speed stays constant. Okay, so these are the things you can remember what happens. So these are the differences. Okay, let's move on. Question 9, blade thickness for axial compressor. So basically the blade thickness for axial flow compressor blade rotors is less than, more than, or equal to axial flow turbines. So this is, so let's say you have a blade like this, so this is basically referring to your blade thickness. Any idea? Like compressor blades have higher thickness, or yeah, it's less. Can you tell me the reason why is it so? Yeah, the correct answer is less. Okay, so let's go to this. So what is the working fluid for axial flow compressors? We have like the cold air, right? So that is the cold air that is coming from the atmosphere. So that is what your axial flow compressor has to deal with. And what is the working fluid for axial flow turbine? That is hot product gases from the combustion chamber. Okay. So just to give you an idea, so the axial flow compressor, the air that will experience the temperature of the atmospheric temperature, so at like sufficiently high altitude it will be like maybe close around 220 Kelvin or so, but the hot product gases that comes out of the combustion chamber, that is over 1500, around 1500 Kelvin or more. Okay, so the axial flow turbine blades are subjected to that high temperature hot gases. Okay, so that's why blades are subjected to high thermal stresses. Okay, so that's why we have to provide them with thicker blades. Okay, so have to withstand those thermal stresses, plus that's why also the blade cooling is necessary, so that the blades does not um, fail under the influence of this high thermal stresses. Okay, so like the turbine blade cooling, that is the that is in the week 12 module. So they discuss about the different methods of turbine cooling. So that is done. One of the reasons that is done is to cool the turbine blades, so that, yes, right, exactly, there are different techniques for cooling the blades. Okay, so that is the reason why. Okay. Okay, all right. So that's why the reason, because we have the turbine blades are thicker than compared to the compressor blades. Okay, all right. Moving on. Okay. So next we have discussion on the other type of turbines, the radial flow turbines. So now we'll do some questions on that. Which of the following is correct for flow through the 90-degree radial turbine? So the options given. Then tell me which is the correct option. One. Okay, let me draw the schematic of this thing again. So in radial flow turbines, what happens, the flow enters radially and then comes out axially. Okay, so it's like the, again, the reverse of what we have seen in centrifugal compressors. Centrifugal compressors, the flow enters axially and then turns over and exits radially. So in radial turbine is the opposite, the flow is entering radially and then come out axially. Okay, so what we have here is, first we have the volute. Okay, so this is volute. So then we have the nozzle. Alright, so then this is the shaft. Alright, okay. Okay, so then we have the impeller, and then the diffuser. Okay, so this is our flow direction. Okay, so first we have volute, then nozzle ring, then impeller, then diffuser. Okay, going by that, option A is the correct answer. Okay, so here I will also, let's label the station number. So volute, or the inlet of the nozzle, is 1, then you have 2, then here this is 3, and finally this is our 4. Okay, so it, like, if you look at this is same as, now if you compare the numbering to the axial flow turbine. So first, in axial flow turbine, first we have the nozzle and then the rotor blades. Okay, so in the similar way, first we have the nozzle vanes here in case of radial turbines, and then the impeller. So impeller is the rotor, right, where the rotating, have a series of blades which are rotating, so that is, or impeller. So it's the same way. So we have first nozzles, then rotor, which is the impeller here. Okay, okay, so let's move on. Question 11. For a 90-degree inward flow radial turbine, okay, so when it's like 90-degree inward flow radial turbine, which of the following is correct for the velocity triangle at impeller inlet? Okay, so here it says that it is saying that we represent the impeller inlet as suffix 1. Okay, so what the where cr is the radial velocity, cw is the wall component of velocity, and u is the blade velocity, v is the relative velocity, and c is the absolute velocity. Okay, so what does it say is that, you look at this. So first we have this, the nozzle blades like this, right? So these are your the nozzle blades. Okay, see again like how I have drawn it, the flow area is converging here. Okay, so these are like the, what you can say, the nozzle ring. Okay. So after that you have your the impeller blades. Okay, so these are like curved, and finally this turns over, and so this like comes in radially and the flow turns and then it exits axially. Okay, so here you are seeing in the plane normal to the flow axis, sorry, the rotor axis. Okay, so here it says that this is your one. So let's say if we draw this velocity triangle somewhere here. Okay, so so you see, so this is, since the nozzle blades are aligned, so nozzle, these are like the stationary blades, the nozzle blades, right? And this is, let's say this impeller is rotating like this. So first we have like aligned along the nozzle blades, the your absolute velocity component will align along that. So this is your absolute velocity component c. Okay, and this so for 90-degree inward flow radial turbines, the blade angle at the blade angle at the impeller inlet is radial. Okay, so the flow here, the relative velocity component will be like this. So this is your v. Okay, and v plus u has to be c, so this is your u. Okay, so this is like station 1, so this c1 u1. Okay, that's okay, just yeah, so is this clear? So because the, for inward flow radial turbine, so the relative velocity component, so the blade angle is 90-degree at the impeller inlet. Okay, so that's why the relative velocity component will be like radial. Okay, so that's why you can say that the cr is our radial velocity component, that is equal to the relative velocity component. Okay, and this will be your alpha 2, sorry, alpha 1, and again this will be your the wall component. Okay, and here you can see that wall component is also equal to u1. Okay, so the correct answer here will be option D. Is this clear? This is how the inlet velocity triangle for a 90-degree inward flow radial turbine looks like. Okay, so the, what's the specialty about this is, the when we say 90-degree inward flow, the blades are radial, so the blade angle is 90-degree, and the relative velocity component is radial. Okay, any question? Okay, so and this is similar to, if you remember, in centrifugal compressors we did something called radial blades, radial bedding. They are also the, so that the blade angle is 90-degree and the relative velocity is radial. Okay, and we had the other different types of blade like forward blading and backward blading, depending on the direction in which the blade is oriented relative to the radial direction. Okay, so 90-degree inward flow radial turbine is that turbine counterpart of centrifugal compressors with radial beds. Okay, here's what I found. So any doubts, question? I guess, I hope the velocity triangle is clear. Okay. Okay, let's move on. Question 12. For inward radial turbine, the velocity in velocity triangles of impeller, the absolute velocity, what happens to the absolute velocity from inlet to outlet? Absolute velocity increases, decreases, remains constant. Option D, fast increase then decrease. What will be the answer here? Just you can answer this similar to what happens in the rotor of, so like the impeller means this is the rotor of a turbine, right? So what we have seen happens in the rotor of a turbine when we did axial flow turbine. So you have seen that in axial flow turbines, yeah, the absolute velocity decreases, right? So in the same way we can say that here also this will happen. So like to just to summarize, we can say that if when we are talking of the rotor of a turbine, absolute velocity will decrease, okay, whether it's axial flow turbines or radial flow turbines, the absolute velocity will decrease. When we are talking about compressors, whether it's axial flow compressors or centrifugal compressors, the absolute velocity will increase, okay. So this you can also again show from the uh, like the velocity triangle as well, okay. So like this was the velocity triangle at impeller inlet, right? So this is our u, so let's say our, so let's get back to this notation that impeller inlet is station 2 and impeller outlet is station 3. So this is impeller inlet, so this is u2, this is v2, this is c2, and then impeller outlet. So in impeller outlet generally the flow exits axially, so we have u3, this is v3, and this will be our c3, okay. So again you can see from the so this is ca3, so the flow is exiting axially. So here you can clearly see that c3 is lesser than c2, okay, and again v3 is larger than v2, okay. So the trends that we see in with the for the absolute velocity and relative velocity components, and that remains same irrespective of whether it's radial flow turbine or axial flow turbine, okay. All right, let's, okay, so these are the important fundamental concepts you should be knowing. Okay, question 13. For 90-degree inward flow turbine, the flow through nozzle ring leads to, the options are increase in total temperature, increase in total pressure, decrease in total pressure. Option D, constancy in total pressure. So question is what happens to the when there is flow through the nozzle ring, which is the correct answer here? Okay, let's look at the options one by one. So first is this one, yeah, option C is the correct answer. So let's go by each option one by one. So like in the nozzle ring, so nozzle, what happens in nozzle ring? So what we know, again I will repeat, the basic working principle of a nozzle is that the static pressure will decrease and the absolute velocity and the velocity will increase. That is the basic working principle of a nozzle, okay. So in nozzle rings, because there is no, so because in, and when there is a nozzle there is no work or heat interaction happening, okay. And if there is no work or heat interaction happening, the total temperature stays constant. Okay, all right. Next, again, the option B is increasing total pressure. This is also wrong, because total pressure can increase only when there is work input. Okay, so if you remember, in case of compressor rotor, across the compressor rotor the total pressure increases because there is work input to the working fluid. Okay, but here there is work out, but in the nozzle ring again there is no work or heat interaction happening, so the total pressure cannot increase. Okay, but what happens is the total pressure decreases. Okay, because so in practical flows, flow through nozzle is non-isentropic, therefore total pressure decreases. Okay, so there is the flow is non-isentropic, and there is no heat and work interaction happening, so the total pressure decreases. Okay, if, but here I have to just that if the flow was isentropic through the nozzle, total pressure will remain constant. Okay, so but we know, in if it's an ideal case, if an ideal nozzle, that will the flow is isentropic, then the total pressure will remain constant. But as we know, in like in practical flows, the flows are non-isentropic, so the total pressure will decrease across the nozzle. Okay, so with this I will just try to recap the radial flow turbine. So the left is, we have the schematic and the velocity triangles that I have already discussed, right? So this is like the at impeller inlet, so the flow is radially inwards. Okay, and this is impeller outlet, flow is axial. Okay, so the flow comes out axially and comes in radially. Okay, and now this is the, let's say this is the, on the rightmost figure is our TS diagram. Okay, so first this is the state point 1, right? This state point 1, what we see is that this is our pressure, the pressure is P1. Okay, and our temperature is here T1. Okay, so then from 1 to 2 is our nozzle, so this is our nozzle. Okay, so the static, so what happens in a nozzle, we know that in a nozzle the static pressure drops. Okay, so the from 1 to 2 you see that there is a dropping static pressure from P1 to P2. Okay, and then and you see also the entropy is increasing. All right, and now if we plot the equivalent stagnation conditions, so this red is our, this is our 0 1. Okay, and this is our 0 2. Okay, so again if you see here, if you let's project this on the t axis, T01 is equal to T02. Okay, because 1 to 2 is our nozzle where our stagnation temperature stays constant, so T01 is equal to T02, and when we go from 01 to 02, we see here that we move from this P01 pressure line to P02 pressure line, and P02 is less than P01. Okay, so we see here with the nozzle the stagnation pressure drops. Okay, across the nozzle. Okay, and all, now if you see the velocities, so you can see here this is our C1 square by 2 C1 square by 2 Cp, and this is our C2 square by 2 Cp. Okay, this vertical is difference, and we know that in a nozzle the flow velocity increases. Okay, so you can see the C2 is higher than C1, which is evident from these green vertical lines, right? Okay, so after that from 2 to 3 we have the impeller, right? So this 2 to 3 is the impeller. Okay, from this is we go from 2 to 3. So this is our impeller. So here we go from this static pressure P2 to static pressure P3. Okay, and now if you look at the the stagnation condition, so we are going from P02 to P03. So this is our 03. So this is P03 here. Okay, so again you can see here what is happening here is that the we have a, since there is like work output. Okay, so the stagnation pressure is dropping from P02 to P03 here. Okay, plus if you look at now the velocities, this is our C3 square by 2 Cp. Okay, so you see that C3 is now less than C2. Okay, that is our absolute velocity has decreased. Okay, all right, and then we have the exhaust diffuser. So in across the diffuser we know that static pressure increases and the uh, static pressure increases and the velocity decreases. That was happens in the finally in the exhaust diffuser. Okay, all right, so yeah, any questions on this? Okay, let's go to the next question. For a radial flow turbine, stagnation temperature of the flow through the exhaust diffuser options are decreases, increases, remains constant. Option D, can't comment. Which is the correct answer? What happens to the stagnation temperature across the exhaust diffuser? Right, it stays constant. Again, why? There is no heat or work interaction. So again, as I have repeated it many times, across nozzles and diffusers, the stagnation temperatures will stay constant because there is no heat and work interaction happening. Stagnation pressure will decrease across both diffuser and nozzles if the flow is non-isentropic. Okay, that is the practical case. Now if we consider ideal case like ideal nozzles and diffuser, then the stagnation pressure will stay constant, but if for non-isentropic flow through nozzles and diffusers, the stagnation pressure decreases. Okay, and when we talk about the static quantities, we have to know the basic working principle of both. For nozzle, the static pressure decreases and the velocity increases. For diffuser, static pressure increases and velocity decreases. Okay, all right. Let's move on. Question 15. For radial flow turbines, which of the following is correct option for degree of reaction? Okay, so let's do this. So first of all, what is degree of reaction? Definition of degree of reaction. So that is equal to static enthalpy drop in rotor by total enthalpy drop, right? Total enthalpy, or just second. Total stagnation enthalpy drop across the stage. Okay, so static enthalpy drop across the rotor for in case of the radial flow turbine, the rotor is our impeller, right? So option A is correct. Okay, so now if you draw the velocity triangles and for the this thing and do some analysis. So what is this? So this is basically T2 minus T3, and this is T01 minus T03, right? Okay, so now if you now do this T0 now for this T01 minus T03, that you can write as so if you go back to the derivation and see that the denominator you can write as CW2U2, okay, and this you can write CW2U2 minus half C2 square minus C3 square. Okay, so and okay, so this and C and CW2 minus U2 is equal to the work done. Okay, and again just go back to the lectures and check how this derivation is done, and this you can get just from the velocity triangles, and then applying the Euler's transformation equation you can get that the work done is equal to CW2U2 if um, flow at impeller exit is axial. So if the flow at impeller exit is axial, the CW3 is equal to 0, and you will get that the work done is just equal to CW2U2. Okay, and this half C2 square minus C3 square is equal to our kinetic energy change, right? Okay, so what we get this other expression is that work done in minus the kinetic energy change based on absolute velocity in the numerator, and again work done in the denominator. Okay, so option B is also correct. Okay, and similarly also one thing you can show this. Okay, let me add okay, so what we have seen is the degree of reaction, that is equal to this thing CW2U2 minus half CU2 C2 square minus C3 square by CW2U2. So where we have seen that this is equal to CW2U2, work done is equal to CW2U2 if exit flow is axial, which implies that CW3 is equal to 0. Okay, so remember work done is equal to U2 C is U2 into CW at inlet minus U2 into CW, sorry, U into CW at inlet minus U into CW at outlet. Okay, that the blade velocity, product of blade velocity into wall velocity. Okay, so if at exit the wall velocity is 0, so the work done becomes equal to CW to U2. Okay, so this is our work done, and this is our kinetic energy change. Okay, so this is work done minus this is your KE change based on absolute velocity, and this is your again work done. Okay, so then again another expression you can show that this is basically equal to half u2 square minus u3 square. Okay, so like while turbomachinery expression was derived, equation was derived, one thing was this was proved that the work done is equal to half kinetic energy change because of absolute velocity plus the kinetic energy change because of relative velocity plus the kinetic energy change because of the blade velocity. Okay, so these are the three components. Like if you remember, one is called the impulse effect, reaction effect, and I forgot the other effect. So these are like the three effects. There was one question I discussed in the week 9 problem solving session. So the work, the rotor work, specific rotor work, we can write as this sum of changes in the three kinetic energies. One based on kinetic energy change based on absolute velocity, kinetic energy change based on relative velocity, and kinetic energy change based on the blade velocity. Okay, so now if from in the numerator we have ws minus kinetic energy change based on absolute velocity, so then we can write in the from this expression we can write it here. So we will have just the kinetic energy change based on the blade velocity and the relative velocity. Okay, right. So the third option is that kinetic energy change based on blade velocity and kinetic energy change based on relative velocity by work done. Okay, so option C is also correct, which means that the correct answer for this will be option B, all of the above. Okay, all right, any questions or doubt in this? All right, let's not delay and let's move on. Okay, so this question 16, for the given expression for blade loading coefficient for inward flow radial turbine, choose the correct option for letter X. Okay, so letter X is our what is asked is our what is the blade loading coefficient. Okay, so so blade loading coefficient again, so this is xi, that is equal to the specific work, right, divided by u2 square. Okay, as I said, we generally use u2 in the denominator. For turbines the u2, u3, u1 all are same, so here you are using u2 square. Okay, and then what is the, yes, right, thank you, half u2 square. Okay, all right, so let's, so then CW, yeah, so here there is to check this. So in the lectures professor have used just u2 square to check whether there is a difference. That just give me a minute. Okay, so I have seen this, the when we do it for when we do it for centrifugal compressor radial flow turbines, is just denominator is showing just using half u2 square, but in case of axial flow machines it's using half u2 square. But okay, let's do it with using half only. So ws will be equal to again u2 into cw2 minus u3 into cw3 by half u2 square. Okay, so you do this will be 0 because there is no exits world. Okay, and then let's say we draw the inlet velocity triangle. So if it does not say like it, since this is not 90-degree inward flow radial turbine, we can just draw a general inflow velocity triangle. So we'll get something like this. V2 U2 C2. Okay, so this is our beta 2 and this is our alpha 2. Okay, and this will be our cw2. Okay, so if we see cw2 is equal to u2 so cw2 has two part, u2 and this part. Okay, so this part, if you see this part, we can write as this is our radial velocity component cr2. This we can write as cr2 cot beta 2. Okay, divided by half u square u2 square. Okay, so now if you take u2 square common, okay, so we will get 1 plus cr2 by u2 cot beta 2. Okay, so you will, if you just cancel, we get 2 1 plus. Now cr2 by u2, this is our flow coefficient. Remember, in radial flow turbo machines, the flow coefficient is equal to radial velocity component divided by axial blade velocity, and in case of axial flow turbo machine, that is equal to axial velocity component divided by blade velocity. So for this radial flow turbo machine, phi is our this thing, and that gives us this times cot beta 2. Okay, so like there is this half term, this 2 extra term coming out. So if you now, because we used half u2 square. Okay, so I need to check these ones because I have seen in the I see in the notes that half u2 square is used when we are doing axial flow turbo machines, and u2 square is just used when we are doing it for centrifugal, like radial flow turbo machines. Okay, so but we are the question asks what is the parameter within cot, and that is beta 2, and beta 2 is our relative velocity angle at impeller inlet. So option B is the correct answer. Okay, so note that here it is written that just inward flow radial turbine is given, so we here draw a general inlet velocity triangle. Okay, so if it's like when it's 90-degree inward flow radial turbine, this beta 2 becomes equal to 90-degree. So when beta 2 becomes equal to 90-degree, so that is just equal to that this yeah, so when beta 2 is equal to 90-degree, v2 becomes equal to cr2. Okay, okay, all right. Any questions? I hope this is clear. Okay, okay, let's move on to the next question. For an inward flow radial turbine, which of the following expression is correct for stage isentropic efficiency eta st? Okay, so 2 and 3 are the inlet and outlet conditions for the impeller. Okay, ca is the axial velocity, u is the blade velocity, and beta is the blade angle, and alpha is the absolute velocity triangle. Okay, so what are we discussing? Yeah, okay, so all right, so now if what is our specific work, that is U2 CW2, right? This is a specific work, okay? And from let's say this is work, this is ideal work. This we can get from thermodynamics, which is Cp T01 minus T03 prime. Okay, so T03 prime is the temperature at the exit of the temperature at the exit of the turbine, given that if the flow is isentropic, right? So this we can write. So our the stage efficiency is defined as the actual work divided by ideal work, right, for turbines. So this is U2 CW2 divided by Cp times T01 minus T03 prime, okay? And so U2 CW2 we saw in this, CW2 is equal to U2, basically U2 times phi 2 of cot beta 2. So this is U2 times 1 plus phi 2 of cot beta 2. Okay, this is what we saw, that CW2 is equal to U2 plus CR2 cot beta 2, and if you now take U2 common, we get 1 plus cot beta 2, and CR2 by U2 becomes phi 2, the flow coefficient. Okay, and in this we take T01 common, so we have 1 minus T03 prime by T01. Okay, all right. So next is this T03 prime by T01 we can write in terms of the pressure ratio. So we get U2 square into 1 plus phi 2 cot beta 2. In the denominator we have Cp T01 into 1 minus P03 by P01 whole to the power gamma minus 1 by gamma. Okay, so the correct option, which is the correct option, is confusing, yeah, the option D is the correct answer. Okay, so this is just the derivation part of it. I guess hope this is clear. Okay, so here we took the work done thing from the this is from our Euler turbomachinery equation, right? Okay, and the ideal work is from thermodynamics, Cp times the change in stagnation temperature. So if the process is isentropic. Okay, all right. Any questions so far? You can just then move on to the next question. So in case of 90-degree inward flow turbine, the degree of reaction is a function of so this will be and go back to a degree of reaction expression. Okay, so we see, if you see the degree of reaction expression here, okay, this one. So we see what we have wall component of velocity, blade velocity, and absolute velocity. Okay, so we have wall component of velocity, blade velocity, and doesn't show a second. Yeah, we can, I guess, use this expression for the degree of reaction. So this has blade velocity plus the relative velocity, the divided by Ws, and Ws is CW2 U2, right? So this is, we have blade velocity u, wall component of velocity cw, and relative velocity v. Okay, so the correct answer will be option 18b. Okay, so let me write it once again. So this we can write as the change in the kinetic energy change because of blade velocity, kinetic energy change because of absolute velocity, sorry, relative velocity, and divided by ws, and ws is cw to u2. Okay, so we have blade velocity u, wall velocity cw, and relative velocity v. Okay, so that's why so the correct answer is option 18b. Okay, okay, so is this clear so far? So any doubts, questions? Okay, let's not delay further. Let's start the problem. Okay, the numerical. So this will be the last question for the day, a numerical on single stage axial turbine. The problem is similar to the one you have in your assignment. Okay, okay, let's see what is given. The total head inlet pressure is 6.5 bar. So this is P01. The total inlet temperature is 900 Kelvin. So this is T01. The mass flow rate is 30 kg per second. So this is m dot. The nozzle outlet static head pressure at mean radius is 1.7 bar. Just read what is there. So the nozzle outlet. Okay, so let's draw what is the turbine stage. So turbine stage, we have nozzle, then rotor. Okay, so this is stage 1, this is station 2, this is station 3. Okay, so it says a nozzle outlet means 2, stay at station 2, static head pressure. Okay, so it means static pressure P2, so that is equal to 1.7 bar. Okay, and mean radius means we know that we do everything, we do the computation, and mean radius Rm, that is 1.7 bar. The mean rotor blade height, the mean rotor blade diameter to height ratio is 15. So what is that means is, so let's say this, we have this, let's say we have a rotor blade, right? Okay, so okay, so the mean rotor blade diameter, so this is our Rm, let's say this is dm by 2, right? So the diameter by 2, and the blade height is this one, so this is b, which is equal, we say, blade height. Okay, so what it says is that this dm, this 15, this is equal to dm by b. Okay, mean rotor blade diameter, this is dm, to height ratio. Okay, then we have nozzle efficiency, eta nozzle 9.95, nozzle outlet angle. Okay, so this is 65 degree. Okay, so so the nozzle outlet angle means the angle that the so nozzle, remember the nozzle blades are static blades, okay, sorry, stationary blades, the stator blades. So the so the nozzle blade angle, the nozzle outlet blade angle will be equal to the absolute velocity angle at station 2. So this will be equal to alpha 2, and I am writing m here because this is at the mean radius. Okay, and we have the Cp is 1147 joule per kg Kelvin, and specific heat ratio is 1.3, because remember we are in the turbine, we are dealing with the hot product gases, so you are using the Cp and gamma values corresponding to that. Okay, so this is clear what is given. Okay, and this is again written, this is like the free vortex, so this is like free vortex bedding. So we know for free vortex bedding, what is the relation? Cw into r is equal to constant. Okay, so the wall component of velocity is inversely proportional to the radius from the rotor axis, right? Okay, so is this clear what all are given? Okay, let's move on. So the first question, question 19a, we have to find out the mean blade diameter of the rotor blade. So mean blade diameter is our dm, right? This one. So this, the mean radius is rm, so and that is dm by 2, so we have to find out dm here. Okay, all right. So so we can find out in this way. So we can write that the mass flow rate m dot, so mass flow rate m dot is, we can write rho 2 a2 into ca, right? So density times the area, so this is like the area of the at the rotor inlet. Okay, times, so the rotor inlet area is like is perpendicular to the axial direction. Okay, and we have to multiply that with the velocity with normal to the flow direction. Okay, so ca. Okay, all right. Now a2 we can write as, so a2 is, we can write as, that is the circumference at the mean diameter, okay, into the blade height. We can write it in this way. A2 we can write as circumference is pi 2 pi rm, okay, into the blade height, that will give us the area. Okay, into ca, or this is like rho 2 pi dm into b times ca. Okay, and now we know that dm by b is equal to 15. Okay, so that we can then we can write dm by b is equal to 15, or then we can write b is equal to dm by 15 ca. Okay, so m dot is equal to rho 2 pi dm square by 15 into ca. Okay, so the again the area a2, we can write it in two ways, like the, if you know, this is like an annular area of an annulus, right? Like we have an outer radius that is at the tip of the blade and an inner radius at the root of the blade. We can do pi times the diameter square at the root tip and minus the diameter square at the root. Okay, but we can also, but we will see that this blade height is generally smaller than the mean diameter, so we can write the area in this way as well. Okay, so pi dmb into ca. Okay, all right. So we know m dot, rho 2 we can calculate if we know the static temperature and static pressure at the station 2, and ca is what we have to compute. Okay, so let's do that. So first it is said that the nozzle efficiency is 0.95. Okay, so nozzle is between 1 and 2. Okay, so now what is the definition of nozzle efficiency? So nozzle efficiency is, if you remember, that is actual kinetic energy change divided by ideal kinetic energy change. Okay, okay, so that is equal to the, remember, that is the kinetic energy change is equal to the total temperature minus the static temperature. Okay, so that gives the kinetic energy change, because the total temperature is equal to this is like cp times this. Okay, that's that the stagnation cp times the stagnation enthalpy is equal to the static enthalpy plus the kinetic energy, right? So that's why the actual kinetic energy change, that should be equal to your the stagnation enthalpy minus the static enthalpy. Okay, so that's what we are doing, and in the denominator we have cp t01 minus t2 prime if it was ideal. Okay, so now the cp gets cancelled. Okay, so then this is t01 minus t2 divided by t01 minus t2 prime. Okay, so then let's say we write t01 minus t2 is equal to eta n t01 1 minus t2 prime by t01. Okay, So T01 minus T2 is equal to eta nozzle. This is what we got. T2 prime minus T01. Okay, now T2 prime minus T01, these we can express in terms of isentropic relation. 1 minus P2 by P01 whole to the power gamma minus 1 by gamma. Okay, now do we know everything? The nozzle we know 0.95, T01 is 900 Kelvin. This is 1 minus P2 is, we go back, P2 is given as 1.7 bar and P01 is 6.5 bar. Okay, this is 1.7 by 6.5 and gamma is 1.33 minus 1 divided by 1.33. Okay, so if we now solve this, we'll get T01 minus T2 as 242 Kelvin. So T2 will be T01 minus 242, so T2 will be 658 Kelvin. Okay, is it clear till this point? So we are starting with the given the nozzle efficiency. We are starting with the definition of nozzle efficiency. So go back how the basic nozzle efficiency are defined in the modules on the nozzles. Okay, so it's like the actual kinetic energy divided by the ideal kinetic energy. Okay, so then we represent that in terms of temperature differences. Then write this isentropic temperature divided by stagnation, isentropic temperature at isentropic exit temperature divided by the total temperature. Okay, so that we can write in terms of the isentropic relationship in terms of pressure ratio, and then we get the temperature, actual temperature difference. Now we know that T01 is equal to T02, right? Because these are nozzles, so stagnation temperature stays constant. So and that is equal to T2 plus C2 square by 2Cp. Okay, right? So this gives us C2, which is equal to 2Cp times T01 minus T2. Okay, so this is 2 times 1147 and T01 minus T2 is 242. So C2 we get as 745 meter per second. Okay, so this is what we get. This is our the absolute velocity at nozzle exit. All right. Okay, so this we obtain. So like from the given the nozzle isentropic efficiency and the pressure ratio across the nozzle and the inlet temperature, inlet stagnation temperature, we can obtain the what is the absolute velocity at the exit of the nozzle. Okay, so now after the nozzle we have the measure the rotor blades of the the rotor blades for our the rotor blades. Okay, so now so let's go back to the expression that we had to get the, so in from this expression we have to find out dm. Okay, so for dm, to find out dm we know m dot. Okay, we have to find out rho 2 we can find out from the ideal gas equation if you know the static temperature and static pressure. So we know the P2 and T2 now, so we can find rho 2, and we have to find out Ca, which is the axial flow velocity. Okay, so for that we have to draw the rotor inlet velocity triangle. Okay, so that is, we have U, then this is our V2 and this is our C2. Okay, so the angles are, this is beta 2, this is alpha 2, right, and this is our Ca. Okay, so if you now look at this, we will see that C2 cos alpha 2 is equal to Ca. Okay, Okay, so this is again, remember, this is at the M, so this is the the angle alpha 2 at the midline, which is the, what do you say, the yeah, the blade angle at the pitch line or the mean radius. Okay, so that, so remember, this is what it is given, the nozzle outlet angle alpha 2, which is 65 degree. Okay, and we know C2, so CA will be equal to C2 cos alpha 2m. So C2 is 745 into cos of 65 degree. Okay, so this will give us CA as 315 meter per second. All right, so here alpha 2 is, m is 65 degree. Okay, is clear till this point? Okay, so we computed the absolute flow velocity using the nozzle using the nozzle isentropic efficiency, pressure ratio, and the nozzle inlet stagnation temperature. Okay, then use the, so that C2, the absolute velocity, is the velocity with which the flow is entering the rotor blade. So we draw the rotor velocity triangle at the inlet, and from that we know that C2 cos alpha 2 is our axial velocity, and we compute the axial velocity. Okay, okay, then you can compute the density rho 2, that is P2 by RT2. Okay, so that is 1.7 into 10 to the power 5. Okay, R is like approx again 287. We can, like, it's slightly different from 287 because it is not air, but 287 is also a good approximation. Like from CP we can compute R also, we can and find out, but what we'll get here is rho 2, we will get as 0.9 kg per meter cube. Okay, so we now know rho 2 as well. Okay, so now we go back to the expression that we wrote here, that m dot is equal to rho 2 pi dm into b, so this is the area, times the axial flow velocity. Okay, and since we know dm by b is equal to 15, we can write this as, this is pi dm square by 15 into Ca. Okay, so then if we, what we have to do, so we have 30, which is 30 meter per second is, sorry, 30 kg per second is our mass flow rate, 0.9 is our density, into pi dm square by 15 into the into Ca, right? So Ca is 315. So if you solve this, you will get dm as 0.71 meter. Okay, so we go down to the options. The option A is the correct answer. Okay, okay, so is the process clear? So we are finding it using the mass flow rate expression. Okay, so we proceeded with, first with finding the, what is the, from first we take the nozzle, the stator stage, the nozzle of the nozzle part. So if there we compute what is the exit conditions of the nozzle, and from that we can get, what we got is the, all the inlet condition, exit nozzle exit condition or rotor inlet conditions. Okay, from that we can find out the density at the inlet of the rotor and the axial velocity, and then we can, using the that mass flow rate is equal to density times the area times the axial flow velocity, we can compute the mean diameter. Okay, all right, moving on to the next part. So this is the nozzle area at the exit in square meter. Okay, so this is now straightforward. So nozzle exit area is our, nozzle area is exit is our A2. So A2 is, we wrote that A2 is pi dm into b. So this is pi dm into dm by 15, right? So this is pi into dm square is 0.71 square divided by, okay, so divided by 15. Okay, so if you Yeah, so annular is this thing, that's what I said. So like you can do in these two in two ways. So so this is so this is your annulus, right? Okay. So yeah, so this is your dm, this is the center, so this is your dm by 2, right? And this is your b. Okay, so one thing you can do is like the, so now if you know this, like this is, let's say, your uh, root diameter dr by 2, and let's say you know this d t by 2. Okay, so then the area will be like this, right? Pi by 4 dr square minus, sorry, dt square minus dr square, right? So you can also so find it that way, or but if the this thickness b is smaller, much smaller than dm, this is a good, also a good approximation, that pi dm into b, this is also a good approximation. This is what we are using here. Okay, see, like if you in this case here, okay, like if you use the area dr by t, okay, like if you now put the area as pi by 4 the dt square minus dr square, okay, and then the what will get will become slightly like, and but you don't know dr and you don't know dm, you don't know dr and don't know dt. Okay, what you know is the ratio of dm by b, and you have seen that dm by b is much larger than 1. Okay, so then in that case this is a good approximation for area. So you take the mean circumference, so the, yeah, the circumference and mean radius, and then multiply it with the thickness. Okay, okay, so like if like you try doing this, the like first part of the problem that way, like taking dr and dm. So another thing is like that dr plus dt, sorry, dt minus dr by 2, that should be equal to b. Okay, so if you like put it here and find it out, you will see that this becomes very, this calculation becomes slightly complicated because this becomes non-linear. Okay, but you know b in terms of dm, so you can just, so this is a good approximation, so that's what we are using here. So if you now do that, we will get a2 as 0.104 meter square. Sorry, I didn't get you. What do you mean? Yes, this is the thing, this your dr by dt by 2, this is dm. Okay, right, and dt minus dr by 2, that is b. Okay, this is right. So now if also you see that if you now put this thing here and this thing here, you will get back this, right? So if you put, see, if you now put dm equal to dr plus dt by 2, and b here as dt minus dr by 2, right? So you will get pi by 4 here, and this dr plus dt into dt minus dr, this is like a plus b into a minus b. What is this? A square minus b square, right? So you will get back this, right? So this formula is valid. Okay, all right, so I hope this is clear. Okay, so why we are using this. Okay, any doubt? till this point. Okay, yeah. So what I was telling, yeah, right. Yeah, so these are the things. Okay, so okay, let's move on to the next question. The absolute velocity angle, so alpha, so at rotor inlet, so alpha 2, but we have to find it at the root of the rotor inlet, at the root. Okay, so that is what we know is alpha 2. We know alpha 2 at the like the at mid radius. Okay, but we have to find it out at the root. Okay, all right. How do we do that? So if we draw, know that tan of the absolute velocity triangle is the this, that is equal to the wall velocity component divided by the axial velocity. Okay, right. So you know, and we know that axial velocity is constant. that that is our, if you know, that is the basic of our derivation also for the free vortex condition, that axial velocity is constant in the flow direction, axial velocity is also constant across the radius. Okay, so the tan alpha 2, the tan of the alpha is equal to the wall component of velocity at the root. Okay, so r here denotes the root of the blade. Okay, all right, divided by ca. Now let's multiply this with the radius at the root, and this is the, we multiply both of these by the radius of the root. Okay, now from free vortex condition, like free vortex blading, we know that Cw into R is equal to constant. Okay, which means that Cw at the root into the radius of the root is equal to Cw at the mean radius into the mean radius, right? So the numerator we can write in this way: Cw2 mean into R mean, and the denominator is Ca into Rr. Is this clear? Okay, so now what is this? The wall component at the mean radius divided by axial velocity. So this should be equal to the absolute velocity, tan of the absolute velocity angle at mean. Okay, and this is Rm by Rr. All right. Okay, so this is our tan alpha 2 at the root. Okay, got it. Next we have to find out what is our all these things. So this is, remember, this is our B. So let's say this is our rotor axis, so this is our Rm, this is our Rr, right? So what we can write is Rm is equal to dm by 2, Rr is equal to dm by 2 minus b by 2, right? So this is the mean. Okay, so this is dm by 2 minus b is dm by 15. Okay, so what we will get is Rr is equal to 14 dm by 30. Okay, so Rm by Rr is equal to dm by 2 divided by 14 dm by 30. So Rm by Rr we will get as 15 by 14. Alright, so then what we have to find out is tan of alpha 2 at the root. that is 15 by 14 times tan of alpha 2 at the mean. This is 15 by 14 of tan of alpha 2, this is tan of 65 degree. Okay, so now if we now just compute alpha 2 at root, this will come out as 66 degrees. Okay, all right. So we see that at the root the absolute velocity angle is higher. Okay, which means, so what we can conclude from that, that the along the as we go along the radius the absolute velocity angle decreases. Okay, so is this clear? So the answer will be option A. So is this clear? So here we are using the fact that it is a free vortex bedding. Okay, and then we are just doing some algebraic manipulation to finally obtain that. Okay, okay, all right. So this is done. Next, okay, this is straightforward. We have to find out the radius at the root, which is RR, and tip of the rotor, which is RT. Okay, so RR we computed just before that, that is 14 by 30 dm, right? This one RR is 14 dm by 30. So and dm is 14 by 30 into 0.7. So RR will come out as 0.33 meter. Okay, and RT, so what is RT? This is our RT, right? Right, and RT is equal to RR plus B. So this is RR plus B, this is RR plus B is dm by 15. Okay, this is 0.33 plus 0.7 by 15. So RT will come out as 0.38 meter. Alright, so the correct answer is option B. Okay, so clear till this point? Okay, okay, I guess this is the last part. Okay, so let's see how, what is, okay, I don't have the solution for this, let's solve this. Okay, so we have to find out the static temperature at the root and tip of the rotor inlet. Okay, static temperature. Okay, so how can we find that out? So T0, so T02 is equal to T2 plus C2 square by 2Cp, right? And T02 will be equal to T01 because this is a nozzle, right? 1 and 2 is a nozzle, so T01 will be, T02 will be equal to T01. Okay, so now we have to know C2. So if we know C2, we can find, so what is this? T2 is equal to T02 minus C2 square by 2Cp. Okay, so now as, so we know C2 at mean. Okay, so as we have seen that C2 changes as we go along the what do you say, the C2 changes as we go along the radius. Okay, so at root, T2 at root will be equal to T02 minus C2 at root square by 2Cp. Okay, so now from, we now go back to the velocity triangle, this one. So we have seen that C2 into cos alpha 2m, that is equal to Ca. Okay, and this C2 that we computed 745, this is at actually at mean radius. Okay, so what we know is, here last part of the problem, C2 at mean radius, that is equal, that is what we know as 745 meter per second. Okay, and C2m tan alpha 2m is equal to Ca. Okay, and Ca we computed as 315 meter per second. Okay, so similarly, therefore at root, C2R into tan of alpha 2R will be equal to Ca, and Ca is constant, so Ca, this is constant at every radius, right? So to find out C2R, C2R is Ca by tan of alpha 2R. So Ca is 315 tan of what was we compute alpha 2R, 66 degree, right? So this is 66, okay, right? So this we get 315 divided by tan of 66 is 140.25 meter per second. Okay, no, this is made a mistake. Sorry. Wait a minute, there is some mistake, I guess. Sorry, this is cos. Sorry, this will be cos. Yeah, this will be cos. Yeah. So what say? Yeah. So C2m cos alpha 2m equal to Ca. So C of cos alpha 2r will be equal to Ca. So this is by cos of alpha 2r. Cos of alpha 2r. So 315 divided by cos of 66. This is like 7 774 meter per second. Okay, so this is our root. Okay, so therefore what we have to find out, temperature at root is equal to T02 minus C2R square by 2 Cp. So T02 is T01, which is given as 900 Kelvin, minus 774 square by 2 into 1147. So square divided by 1147, square divided by 2 divided by 1147, yeah, just second, I'm getting 640. Just let me check if I got this wrong. This is cos, sorry, 315 divided by cos of 66, right? Okay, so this is 774.45. okay, so this square divided by 2 divided by 1147 minus 900. Yeah, now I got it right. So okay, so I'm getting 38 Kelvin. Okay, or like, yeah, so this, the closest answer I have is 629. There might be a typo here. Okay, okay, but the thing is, so now that's how we get it here at the root. Okay, so now the next step is, like, if we find alpha at tip. Okay, so once we find alpha at tip, we can find C2 at tip as Ca by cos alpha 2t. Okay, and then we can find the alpha 2 at tip in the similar manner. Okay, so yeah, and then that will give you the answer. Okay, as I think this, you have to check that, but that is like the correct answer. The option showing is will be option D. Okay, so but is slightly wrong stuff here, but okay, but this is the idea. Okay, any, yeah, so any questions, doubts? So what we did here is, because the to find out the static temperature is equal to sorry, this is stagnation temperature minus C2 square by 2Cp. Okay, so and C2 changes at each position. So first we find out the what will be the C2 at that radial position. Okay, so given the knowing the angle at that position, so and the axial velocity, which is constant across the radius. So once we know the absolute velocity at a particular radius, we can find out what will be the temperature at that radius. Okay, so if we found this out for the root, similarly if we repeat the procedure, like find alpha 2t, so like in the similar way we find out alpha 2r, so in the same way, like this way. So here in the like that so in this way, like we find out tan of alpha 2 at the root is equal to tan of alpha 2 at mean divided by Rm by Rr. Similarly, we can find out the tan of alpha 2 at tip, which will be equal to tan of alpha 2 at mean radius into Rm by Rt. Okay, in that way we can find out the angle at the tip. Okay, the absolute velocity angle at the tip. From that we can find out what will be the absolute velocity component at the tip. Okay, and then we can proceed in a similar manner to find out the static temperature at tip. Okay, so I'm not skipping the last part. Okay, but I think you got the idea. Okay, so any questions or doubt regarding today's session? I can't this is like this NPTEL have scheduled like this for like 12 sessions only. So but I will, in the next week I will try to cover yeah, the most of, like, do most of the time covered in the some revision of the topics. Okay, because the week 12's module, that content is like very small and mostly theoretical. Okay, so like we'll do a few MCQ type questions on that, and then move on to revisions of the things we have that has been covered throughout the course. Okay, anything else? Okay, if there are no further questions, we can end today's session. So I will meet you again next Monday at 6 p.m. 6 to 8. That will be the last live session for this course. Okay, so I will discuss the cascade and the turbine cooling part, and then do a bit of revision of the revision questions and revision problems from all the topics discussed in this course. Okay, all right, so I will close today's session. Thank you for attending. Have a good week, and see you again next week on Monday. Good night.